Hello, everyone, and welcome to the course Reasoning Based LLMs from Scratch. In this lecture, we are first going to do a quick recap of where we are at the moment, and then we are going to cover the two main sections which have been planned for this particular lecture. Remember, we started out with this question that human beings have this incredible gift of being able to think deeply, and it is something which is happening in that tiny little brain of ours, which allows us to navigate our way in this world which is highly complex. And we had looked at a simple example of ordering a cake for our mother on her birthday, and we realized that this is not a simple task, and we consider a lot of thoughts in our mind before we order the right cake. And this process is what we call as reasoning. Um, and there are two types of reasoning. There is fast reasoning and there is slow reasoning. So let's say if someone asks me the question, "What is the capital of India?" I can immediately think of the right answer. But if someone asks me the question, "Which movie shall I watch tonight?" This is not a straightforward answer to me. I take a long time to answer this question. So this is also called as system 1 and system 2 type of thinking, where system 1 allows us to respond rapidly to questions, and system 2 is rather slow and deliberate, which takes its own time before it answers. Now, the main question was that when ChatGPT was first released, it was great at System 1 tasks, but it performed poorly on tasks which required complex reasoning. And that's the reason human beings set out on this quest to build these large reasoning models, which are LLMs, which could reason like humans do. And OpenAI's O1, which was the first model which was released in this category, and it appeared to reason before it gave you the answer. But the question was, it was completely a black box. People did not know what was happening inside OpenAI's O1. Uh, all we knew was that it was performing well on complex reasoning tasks. But DeepSeek R1 opened the Pandora's box, and it really told us what exactly was happening uh, with OpenAI O1. It gave us a recipe for building reasoning models, and that's where this course was conceptualized, and we wanted to bring this recipe to as many people as possible. So the recipe largely involved four ingredients, which became the blueprint for building a large reasoning model. Ingredient number one, which were the first three lectures of our course, focused on inference time compute scaling, which means that if you allow a large language model more time to come up with the answer, it generally performs better. And this is inspired from humans. If, let's say, we are solving complex puzzles like Sudoku, if we are given more time, we generally do better in most of the cases. Now, people thought that what if we can make LLM think before giving an answer? And if we take a simple example like this, Roger has five tennis balls. He buys two more cans of tennis balls. Each can has three balls. How many tennis balls does he have now? A regular LLM uses only three tokens, it directly gives us the answer. But a reasoning LLM shows us all the intermediate steps before it gives us an answer. So it is using a lot of inference compute. And that is why the name inference time compute scaling comes from. It is because the accuracy of the LLMs can be shown to scale with the test time compute, and this was not very intuitive. When we started building LLMs, people largely focused on pre-training and fine-tuning, and very less importance was given to the inference stage. But now people understand that giving more time to inference is actually making my model better on these reasoning tasks. And then this was first thought of in 2022 by the brain team at Google Research. Google gives us some wonderful innovations over the years, and this is another one of their team where they showed that if you just include the chain of thought in the prompt itself, then that will serve as a guide which will allow the model to think that, okay, the user has given me a prompt which looks something like this, and maybe the user is trying to tell me that I should provide some chains of thoughts before I give an actual answer. And that is exactly what it does. Uh, at the bottom, you can see the question is the cafeteria had 23 apples. If they used 20 to make lunch and bought 6 more, how many apples do they have now? And standard prompting gives the wrong answer, but chain of thought prompting gives us the correct answer because it shows us the multiple reasoning steps which the LLM goes through before it comes to the right answer. And that is why the name is given as chain of thought prompting. It does consume some more computational resources while inference, but it gives us better answers. And then someone said that, can we make it even simpler? Can we, without taking this much effort, let's just add the following line to the prompt. Let's think step by step. And it worked beautifully. Sometimes simple solutions work very well. So this is another example in test time compute, chain of thought, zero shot. There is another technique called tree of thought. And then there are verifiers, which we had discussed before, best of n, beam search, and look ahead search. What verifiers do is that you tell the LLM that generate multiple answers, don't just generate one single answer, and then choose the answer uh, which has the maximum reward, or which is voted by the reward model as best most of the time. I'm using a different terminology called reward model here, but the main essence of verifiers is to make sure that uh, you are being shown the answer which is the best answer among multiple reasoning paths. So it allows the model to explore multiple reasoning paths and then give you the best answer. Okay, so this was the first ingredient, which was test time compute. The second ingredient is pure reinforcement learning. We have spent the last 18 lectures discussing about pure reinforcement learning. And the whole journey has been in such a way that we started with classical reinforcement learning, where we learnt about um, the agent environment interface. We understood uh, uh, how reinforcement learning problems are modeled, what are the different algorithms which are used to solve RL problems. And then slowly we move to function approximation methods, which included value function approximation and different types of policy gradient methods. And then finally, we focused on how to apply these reinforcement learning techniques in large language models. And there we looked at proximal policy optimization and group relative policy optimization. The GRPO algorithm was at the heart of the first model which came out of DeepSeek R1, which was DeepSeek R1 0. And they showed that, uh, without explicitly teaching the model how to solve the problem, it can automatically develop reasoning strategies on its own. So there is a very nice example which is highlighted in the paper. It is a mathematics problem where we are asking the model, if a is greater than 1, then the sum of the real solutions of this equation is equal to what? And the model starts to think in a specific path, and then it slowly realizes that that path is not correct, and let me reevaluate what I did and follow a different path. And this is a very human like quality. We have this ability to self reflect on our thoughts, and that is exactly what DeepSeek R10 model did. And this model was trained using pure reinforcement learning. We did not give any input output examples, and told the model, okay, learn from these examples and behave accordingly. But the model learned these capabilities on its own. And throughout this course, the 18 lectures that we have taken in reinforcement learning, we have really understood the nuts and bolts of this entire process. We have understood where the field of RL started and where it has been taken to now, and the series of different innovations which have happened along the way, which has really contributed to reinforcement learning being at the center of reasoning large language models. Okay, so this covers ingredient 1 and ingredient 2. And now in today's lecture, we are going to focus on the remaining two ingredients, which are ingredient number 3 and ingredient number 4. Now, both the ingredients that we have looked at so far, they are good for inducing reasoning in a model, but they are not production level. In other words, these ingredients are not enough to make a dish which people will enjoy. And the reason is that DeepSeek R10, even though it was good at reasoning tasks, it had this issue of language mixing. And several times, what happened was that the model mixed multiple languages in the output, and it was not good at general purpose tasks. It was only good at some complex reasoning tasks. And that is the main reason why DeepSeek R1 was developed. And ingredient number 3 is going to focus on this exact same thing. We are going to understand how is DeepSeek R1 exactly different from DeepSeek R10, and what qualities make DeepSeek R1 production level compared to DeepSeek R10. We have already seen that DeepSeek R10 has this issue of language mixing, so it cannot be deployed to user-centric applications or platforms. So now let us try to understand the different steps which are involved in building the DeepSeek R1 training pipeline. And through this, we will understand the process of supervised fine tuning and reinforcement learning. So let's get started. Okay, so in the previous lectures, what we have seen that pure reinforcement learning is used to build a model called DeepSeek R10. And the process looks something like this. You have a bunch of questions, uh, which is a question bank. And this question bank is given as an input to the model, one question at a time. The base model which we are using here is called as DeepSeek V3. And since this is a large language model, it will give a prediction for the next best token in the sequence, and it will generate multiple outputs at a single time. So, totally, there might be 10 or 15 outputs it generates. This is one of the uniqueness of the GRPO technique. And then what it does is all these responses are ranked, and the ranking is done based on the accuracy of the answers. If the answers are very accurate, uh, then they get good rewards. If the answers are not accurate, they don't get good rewards. And we do not need a reward model in this case. All we need are rewards which can be verified. For example, coding problems can be verified using the lead code compiler. Mathematics problem, arithmetic problems can be verified by the calculator tool. So as long as we have tools which can verify these outputs, we do not need a reward model. And then after these rewards are calculated, we use these values to calculate the advantages for all these different outputs. And these advantages are then used to calculate the gradient of the surrogate objective function, followed by a gradient ascent method, which is used to update the large language model. So we are making the large language model better and better and better based on the rewards which the outputs are getting. And this is nothing but the GRPO algorithm and the reinforcement learning pipeline which I am showing in this diagram. In case this diagram is complicated to understand, please have a look at the GRPO lecture, which is outlined as a part of this series. So this is step number one. Now, as explained before, the model that we get out of this step is not very practical. It is not something which can be deployed in a user centric setting because it has this issue of language mixing. So then, what people do is they collect a lot of data from the DeepSeek R1 model. And how is the data collected? Well, the data is collected by asking a bunch of questions in the prompt and then giving a chain of thought or giving a set of examples in the prompt itself. So this is called as few shot learning. For example, if the question is translate English to French, and then you give a bunch of examples. Sea otter, how is sea otter translated from English to French? How is peppermint translated? How is plush giraffe translated? And then you ask the question that how is cheese translated from English to French? Similar to this, there might be a lot of other questions you might ask, and people generally collect around 1000 to 2000 examples of input output data by asking these type of questions to DeepSeek R1 model. So this is very similar to the chain of thought example which I gave at the start of this lecture. Now some of you might be wondering, why do we collect this data and why is it called cold start data? Well, the reason is that DeepSeek R1 is directly trained on the base model DeepSeek V3. But we don't want to do that. We want to use this reinforcement learning step on a model which is not the base model but slightly better than the base model. And that's why we collect this cold start data. So this terminology I think comes from the cold starting an engine, which means that if the engine is at a temperature which is less than the ambient temperature, then you can cold start it to get it going. So in the next step, what we do is all this data that we collect, we fine tune the DeepSeek V3 base model based on this data. And we get another model which is called DeepSeek V3 fine tuned one. Now, what is this new word which I have introduced called fine tuning? Fine tuning is very similar to supervised learning. You have input output pairs of examples and you are training the model to understand those examples. For example, here I have these n examples as I've given 1, 2, 3, dot, 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 n. Example 1 illustrates how sea otter is translated from English to French. Example 2 illustrates how peppermint is translated from English to French. And then example n illustrates how plush giraffe is translated from English to French. After each of these examples, there is a gradient update step which tells the model that uh, if you are giving an output which is different than what I am showing you, then you update your gradient and then change the weight parameters of the neural network. And this happens multiple times for all the examples which I am providing. This is very similar to how a neural network is trained on a series of input output pairs of data. The only difference is that here the pairs of data are collected from the DeepSeek R1 model. Okay, so now this is the fine tuning step. We have fine tuned the model using our cold start data. And then again, we perform the reinforcement learning step here. This is the same GRPO pipeline which I had showed in step number one. The only difference is that The model that we are using here is not DeepSeek V3 but DeepSeek V3 fine-tuned one. If you are watching closely, you might have noticed that there is another difference in this figure, which is not very apparent, but if you watch closely, you can see there are consistency rewards being added here. What are consistency rewards? Consistency rewards are rewards that check whether the output which the LLM is giving, is it mixing multiple languages or not? If the output is mixing multiple languages like let's say Hindi, English and French, then the output is penalized. If the output is in a single language, then it is not penalized. This ensures that the drawback of DeepSeek R10, which was language mixing, is completely taken care of. So this is also called as consistency rewards, which is added to the accuracy and the format rewards which were described previously. Everything else remained the same. Now you might ask, okay, are we done here? Is this what DeepSeek R1 is? Well, the answer is no. We have a few more steps remaining, which are very similar to what we saw before. This might remind you slightly of convolutional neural network where we have these layers, right? We have uh, initially the convolution layer, then the ReLU layer. Again, we have the convolution layer. Again, we have the ReLU layer. So the process repeats. And the reason it repeats is because every time you go through the process, the model becomes better than what it was before. So now we are going to do the same thing again. We are again going to collect a lot of data. And this time we are going to collect data from this fine-tuned model, from this model which has been generated from this step. We are going to collect 6 lakh examples of input output reasoning data. And we are going to also use the DeepSeek V3 base model to collect 2 lakh examples of input output reasoning data. So that is a total of 8 lakh examples of input output pairs of data. This is huge compared to the cold start data which we had collected before. And the reason this data is collected is because remember I had told you that DeepSeek R10 is not good for general purpose tasks. To make the model general purpose, we have to provide filtered examples which are giving correct answers and then train the model again on it so that the model performs better on these filtered examples. And these filtered examples can represent wide range of domains like law, then let's say medicine, biology, etc. It can represent multiple different fields. And you might have guessed the next step. Again, we are going to do fine tuning, but this time we are going to use 8 lakh data samples. So imagine the amount of gradient update steps we are going to require for this fine tuning. And then after the model is fine tuned, we get DeepSeek V3 fine tuned 2, which means that the model has gone 2 rounds of fine tuning totally. And then again, we perform 1 round of reinforcement learning. And this time, the difference is that the model which is located here is DeepSeek V3 fine tuned 2. And again, we have made some changes in this reward box. We have added this reward model. Why we have added reward model? Well, the reason is that if you ask questions which are subjective, if you ask uh, this model that generate a poem about the beauty of sunset, you cannot use lead code or any tool to evaluate that because the question itself is very subjective in nature. So you need a reward model which is trained on human preferences. So in this final RL step, you have accuracy, format, consistency, rewards, but you have a trained reward model also, which is used to generate rewards on questions which are subjective in nature. And then the rest of the GRPO pipeline remains exactly the same. So These are the 7 steps, and at the end of this, you get a model which is called as DeepSeek R1. This was the model which completely blew the world because it gave us the recipe on how um, reasoning models are built, and it was competitive to OpenAI O1. It was comparable in almost all of the benchmarks, and in some benchmarks, it was even better. So, there are 7 steps which are involved totally in this whole pipeline, and that is why this process is called supervised fine tuning and reinforcement learning. That is where this name comes from, because we have 2 rounds of supervised fine tuning and 3 rounds of reinforcement learning in the entire process, including the round of reinforcement learning which involves the training of DeepSeek R10. Now we come to ingredient number 4. Ingredient number 4 is called as distillation. You might have heard of distillation in the context of water purification, but distillation in the context of building a reasoning model means something completely different. And let's try to understand what it means over here. So, in the context of reasoning LLMs, it means the following. Let us say that we have a small model which does not have reasoning capabilities. Let's say we take the example of a model like Quen 2.5, which is a model which has 3 billion parameters. Now, the question is, how do I give reasoning capabilities to this small model? This is the question that I want to answer. You might say that, okay, why don't you just switch your model to a larger model? Why do you need this small model? Well, the reason I need the small model is because I want to run this model on locally on my hardware, and I do not have a very sophisticated hardware which has a lot of memory. I'm using a simple laptop, and I want to run this model locally on my laptop. I do not want to use external providers like ChatGPT, but I want to run it locally. Now, to run it locally on your system, you cannot have a model like DeepSeek R1 because it has 671 billion parameters. You would run out of memory very fast. So, so now you cannot say that just switch your model to a larger model, because I have this constraint of putting my model into the existing hardware which I have. And then the next question is, okay, then what is the solution to this? And this was provided within the DeepSeek R1 paper, in which they said that what if we do something like this? What if we use the data set from a larger model which has reasoning capability, and then we use that data set to train the small model without reasoning capability? Will that work? uh, I'm pretty sure that before they got the results, they were not very sure whether this approach would work or not. But it turns out that this approach does work, and you can actually give reasoning powers to a small model uh, by using a data set from a larger model. So this opens up the door for building models which are good at solving complex reasoning tasks and which are perfectly compatible with your hardware. So I really believe that the process of distillation will be used a lot in the future when we make when we make devices for consumers in which the LLM will be loaded directly in the device. You would not have to connect to the internet every time to access the large language model. Just like we have a CPU sitting in our system every day, we don't pay for uh, accessing the CPU compute for every single token. Similarly, there will be an LLM which will sit in your device, and the process of distillation will be the key for bringing LLMs, bringing the reasoning power of LLMs to smaller models. Now, how did they do this? Well, first, remember the 8 lakh input output pairs of data which we had generated uh, in step 4 or step 5 of the ingredient number 3, which was supervised fine tuning and reinforcement learning. Well, this exact same data is used to fine tune a smaller model, which is Quen 1.5 billion. Now, remember that DeepSeek R1 used 671 billion parameters, whereas Quen only has 1.5 billion parameters. So, this model is 450 times smaller than DeepSeek R1. And then, yet, after fine tuning, they found out that this model does acquire reasoning powers, which was really mind blowing. And if you look at the metrics, these are the different metrics. So this is the DeepSeek R1 Distill Quen 1.5 billion. On most of the metrics, it does better than GPT-4o. Now, this is a model which is 450 times smaller than DeepSeek R1, and still it is beating GPT-4o in majority of the benchmarks, which is absolutely amazing. And again, as I said, this method will be the future to make LLMs available on our personal devices like phones or laptops. And this was ingredient number 4, which is used to build a large reasoning model. So let me recap the ingredient number 3 and ingredient number 4, which was covered in this lecture. The third ingredient was supervised fine tuning and reinforcement learning, where we did supervised fine tuning 2 times, followed by 2 times of reinforcement learning. And this made sure that we had a model which was good for general purpose tasks and which did not have the issue of language mixing which DeepSeek R10 had. And then ingredient number 4 is the process of distillation, using which we can give reasoning powers to smaller models by using data set from larger models and then feeding it to the smaller models. So, this brings us to the end of today's lecture. And with this lecture, we have covered all the 4 ingredients uh, which were shown to all of you at the start of this course. And now we have a very firm and deep rooted understanding of all the 4 ingredients or modules which are used to build a reasoning model from scratch. Thank you very much, everyone, and I will see you in the next lecture.